What's up guys, and welcome to another video solution. This time I'm going to solve the problem 75, which is the problem about a set of wires, sorry, not wires, but spires, a set of spires, which is, it's actually called a coil. Since I'm not a native English speaker, I don't know, I forgot these names. Anyway, and there is a wire with a current passing through it, right above the spires. So we have to assume that the wire is in the same plane as the coil, or as the spires. So we have to think that the spires is very thin, much thinner than the wire itself, than the diameter of the wire. So anyway, this is just a comment. The only thing we have to determine is the what we call multi-inductance, or I think maybe multi-induction. I think multi-induction is the right name. But anyway, as I told you before, I'm not a native English speaker. But anyway, I'll call multi-inductance. So, in order to determine the multi-inductance, we may remember that the definition of the multi-induction equals, in this case, where there are any spires, we have n factor here multiplying the magnetic flux across one of these spires divided by the current, which is responsible for the variation of the flux in that spire. And another thing that we could do, which actually is the same thing, because in any of these approaches we have to determine the magnetic flux. We may consider that the factor which relates the electromotive force with the derivative of the current with respect to the time is the factor m. So this is a proportionality factor. So and this derivative remembers acceleration, but anyway, that doesn't matter now. So we have to determine the magnetic flux, which equals the magnetic field at the position. I'll call this is zxy. So this is the magnetic field at x equals 0 times, or better, vector product dA. And maybe consider dA as you take a strip, and if you are seeing the figure, the strip has length L, and this is dz. So maybe you consider dA equals L dz. And we consider also that J is the same direction as B. So the magnetic flux, and B, we know B because we know Ampere's law, and the magnetic field generated by the current is actually magnetic permeability times the current divided by 2 pi divided by the radial distance from the wire, or the path of the current, times the radial vector, and this is a vector. But since we are in the plane of the wire, this R equals Y. And I think this radial vector equals X, if I'm not wrong. In this element of area, there's an X vector X here. So everything okay. Now calculate the magnetic flux. We get this thing, magnetic permeability times the current divided by 2 pi. There is another factor here. I think there is Z here and divided by Z here. Sorry, I put the wrong thing. I made a mistake. This is Z. Here is Z. And we are calculating from A to A plus B. So we get Let's do this fast. This is the expression for the magnetic flux, and to determine the multi-inductance we multiply by the factor n, so there is no magic in here. A plus b divided by a, and divided by the current, actually, because there is a current. If you see the first equation that I written, sorry, there is a factor current here, and this current cancel out with this one. So this is the expression for the multi-inductance, and we just have to multiply the quantities, which is a thing from high school. 10 to the minus 7. I think this is Henry per meter. Actually, there is meter here, so meter cancels out with meter to minus 1. If you see the figure, you will note that a plus b equals 9, because b is 8 and a is 1. So we get 9 over here, divided by 2 pi, and we get a multi-inductance of the order 1.32. This is 2. Oh, became worse. 132 times 10 to the minus 5, and this is Henry. I hope this is the right unit. Anyway, this is the multi-inductance. And the other approach we could do actually is the same thing, because anyway we would determine the magnetic flux, and from the magnetic flux we could determine the electromotive force, because we know that the electromotive force right here, down here, the electromotive force is the negative, or the derivative of the flux. And if you see this expression, when you derive this expression with respect to the timing, actually the current, the only thing which depends on the time is the current. So you get a derivative of the current with respect to the time. So you get an expression like this one, and the proportionality factor equals the multi-inductance. So this is anyway almost the same approach to do. So guys, this is it. I ask you if you see some mistake or something is not clear. I ask you to comment on this video. I also hope that you have enjoyed this video, or at least not feel bad for this. I also hope you have a good day, and I think I'll see you in the next problem. Bye bye.